In this HVAC training video, we're going over microchannel coil in an HVAC system, and we're going to go over how it works and how this coil differs from, say, a copper tube and aluminum fin or an aluminum tube and aluminum fin heat exchanger. To give you a tour, we have high pressure liquid entering the metering device and then low temperature saturated refrigerant exiting. So that's a mix of liquid and vapor in this tube before it enters this header section, which we cut open so that you can see it. And so that refrigerant's actually going through that little tube with all the little slits and filling the header tube before it then enters into those little channels. After the refrigerant exits through this little slit and gathers into the main header, it's going to enter into these main channels. And so these main channels are about 1 inch long, and so you're going to have about 20 to 30 little microchannels. And so this one has 25 little tiny pathways for the refrigerant to travel through. And so this one has 41 main channels. So we take 41 times 25 and we have 1,025 little pathways for the refrigerant to travel through from the saturated side over here all the way up in one main channel over to the suction side of this coil. On the vapor suction side of the coil, we have the vapor refrigerant exiting through each of these little microchannels, entering into the header, entering through the little slits into the suction line where it's then going to exit the coil. So now when the coil is connected to a whole system, obviously you'd have to have the door here because you're going to have air going through the coil fins and traveling up to the blower and out of this air handler that we have here, but you'd have high pressure, high temperature liquid refrigerant entering the metering device, and you'd have saturated refrigerant exiting the metering device. It's going to be low in pressure and low in temperature. So then it's going to come into the header, it's going to go into the microchannel coils, and it's going to go all the way through each one of these, and it's going to be traveling upwards. And so it's going to be maybe, say, 20% vapor, 80% liquid as a saturated mix, and it's going to travel upwards. It's going to be maybe, say, 38 degrees or 42 degrees or something like that. It's going to be staying just at that temperature as the phase change is occurring. And so by the time the refrigerant travels up to here, maybe it's now at, say, a 50-50 mix, 50% vapor, 50% liquid, still at, say, 38 degrees. It's then going to travel this way. It's going to be, say, 75% vapor now, 25% liquid, and then it's going to be, say, 90% vapor, 10% liquid, and then a fully 100% vapor refrigerant. So this whole section of the coil all the way over to here is going to be, say, 38 degrees. So this entire thing is 38 degrees. All of it's 38 degrees as the air is going across it. Then it's going to change completely into a vapor state, and it's going to increase in temperature. Maybe it changes to, say, 50 degrees for the temperature of the vapor as it's exiting. So that'll be a 12 degrees of superheat as it's then exiting and heading back over to that vapor compressor. So this is a microchannel coil, whereas this one right here is an aluminum tube and aluminum fin, and it has an aluminum plate. And this is the older conventional one where you have the copper tube and aluminum fin with the galvanized plate. A lot of times these rust and you end up having a leak down here at the lower section, so that's been an issue. So both of these have a thermostatic expansion valves instead of a piston metering device like we were looking on the previous example, but the premise is still the same. So you have your high pressure liquid entering, and then you have low pressure saturated refrigerant exiting. And so it's going to exit through these distributor tubes over to the coil, and then there's going to be 4 tubes that the refrigerant is going to be traveling through the coil. On this one, there's 6 tubes right here, so 3 here and 3 here. So it's going to be traveling through 6 tubes, 3 on each side as the refrigerant's traveling through. Whereas with the microchannel coil, there was 1,025 pathways for the refrigerant to be traveling through those little microchannels. And so you have, say, 80% liquid, 20% vapor here, then maybe a 50-50 mix. So this would all be, say, 38 degrees. And then you're going to have, as you have air traveling through this coil, you're going to have a phase change occurring. So then you're going to have, say, 75% vapor, 25% liquid, and then you're going to be fully in the vapor state by the time you get up to here on this coil. So the phase change is occurring from here up to here on both sides, and then it's completely in the vapor state. Say it increases from, say, 38 degrees up to, say, 50 degrees, and then the vapor gathers back into the header tube and travels back to the compressor. So that's how this differs from the microchannel coil, because the phase change is occurring on both sides up to this point, and then it's vapor here and here. Same thing here. So the phase change is occurring from here all the way up to here, and then it's vapor from here up. And so these tubes have rifling on the inside to increase the surface area. Similar to these, they also have rifling on the inside, and these fins themselves may have little tiny cuts in them as well to increase the surface area and heat transfer. Very similar to the little cut that there is in the fins on the microchannel coil. The purpose of a microchannel coil is to have very good heat transfer while also reducing the refrigerant charge. So they're going to have, say, 70% less refrigerant traveling through them than the conventional type of coils like the aluminum tube and aluminum fin. And so that's the whole point of it. And so the indoor coils are not necessarily as prone to corrosion than the outdoor coils. So an outdoor microchannel coil, you want to maybe not install that if you're near the shore, just due to the salt air. You end up having leaks from those. But inland, microchannel coils are fine. Now this one right here is a conventional copper tube and aluminum fin. And so these will hold up, and you can pump a system down like this potentially, say if it has a reciprocating compressor or something like that. But if it has a scroll compressor, you don't want to pump it down all the way anyway. But if it's a microchannel coil, you definitely can't pump it down because you have those tiny little pathways in the tubing of the microchannel coil. So if you try to force all the refrigerant from the entire system into the outdoor unit that has microchannel coil, imagine those tiny little pathways are going to get filled with liquid and then overpressurized, and then they're going to burst. And so that's the issue. And so if the coil is designed for 70% less refrigerant and the indoor coil is 70% less refrigerant, you're still going to have refrigerant, a decent amount traveling through the tubing. So you might end up with, say, 40% less refrigerant for the entire system, or maybe 50% less refrigerant for the entire system. So that's the whole point, is to increase heat transfer. The issue is, as you're seeing these little tiny pathways, there's not much aluminum there as far as the high pressure, and also if there's corrosion, that's going to be an issue. But if you do have a leak with microchannel coil, you can fix it. After you recover the refrigerant out, you can use an aluminum soldering rod in order to fix that leak. And if it does clog off that channel, it's not that big of a deal because there's 1,025 of them, right, in the example that we were looking at. And so you'd use the same rod to fix a leak with this as you would with the aluminum tube with aluminum fins. Now, an evaporator coil that's microchannel, we don't seem to be having that much trouble with those as far as leaks, but if you live near the coast and you have microchannel outdoor coils, that may be a problem. At least in my experience, I've seen a lot of leaks occurring due to the thin outer wall of the microchannel coil, even though they maybe are cladded with zinc in order to protect from corrosion. The whole point of the zinc coating on the microchannel coils is to be able to have a lateral corrosion. It's like a sacrificial anode almost. It wants lateral corrosion instead of inward corrosion, where an inward corrosion would end up having a refrigerant leak. So you got to think the outdoor unit of an air conditioner is higher pressure, and it's in a salt air environment or maybe an acidic environment where you have leaves going down in there, and you may have a problem at the lower section due to leaks. So a lot of times we're installing either the copper tube and aluminum fin, or now we're installing the aluminum tube and aluminum fin, and those once again are also dipped in zinc a lot of times. So it's just something to be aware of. I hope this video on coil types and microchannel coils has helped, and if you want to learn more about HVAC, make sure to check out our new 2nd edition Refrigerant Charging and Service Procedures for Air Conditioning book. So if you want to learn about refrigerant handling and pressure testing a system, vacuuming, breaking the vacuum with refrigerant from the bottle or from the system, refrigerant charging on a running system, charge indicators for troubleshooting, measuring airflow, and a lot more, make sure to check out our new 2nd edition book, which is available over at acservicetech.com, TrueTech Tools, and on Amazon. Hope you enjoyed yourself. We'll see you next time at AC Service Tech channel.